Hi friends, welcome back to our case study videos. We are discussing our first case study on reactor yield. We are in the measure phase in which the team has done basically two things: validated the measurement system for primary metric and identified causes and shortlisted them. For validating measurement system, the bias and linearity study was done, and also gauge repeatability and reproducibility study is done. For identification of the causes, team used process flow diagram method, and for shortlisting, cause and effect matrix was used. The measurement system study starts with bias and linearity study. And even before bias and linearity study, we have to define the operational definition of the measurement system. The team tried to define the operational definition, and they understood the yield is calculated based on the concentration of the required material in the chemical, and concentration is calculated by titration. So the measurement system analysis or bias linearity study was to be done for entire titration system. The team then calculated the standard deviation of the past data, and they found it is 4.3, and based on which they took mean plus 3 times standard deviation, which is upper control limit, and mean minus 3 standard deviation, which is lower control limit, and they took 10 samples between lower control limit and upper control limit. These 10 samples you can see varied from 61 to 75, and team started taking data on these 10 samples. So each of these 10 samples was measured using a very good inspector, and the readings given by the inspector were again compared with the master readings. The difference between the master reading and the reading taken by the inspector is called as bias, which you can see in the form of blue dots in the graph, where each blue dot indicates the difference between the measured value and the true value. Now the average of this is shown by the red dot, and a trend in the red dot is shown by the red line. The line seems to be little tilted, but let us see if the slope of the line is significant or not. We see here that the slope is not significant because p value is much higher than 0.05 in case of slope, as well as we see p values of each of the bias is insignificant because all of them are more than 0.05. So all in all, there is no linearity issue and no bias issue with the measurement system. Now we will initiate our GRR study, also called as gauge repeatability and reproducibility study. In this study, we will first define specification in equivalent terms. For example, what yield is equivalent to what concentration? We found that in terms of concentration, the specifications, lower specification is 52.5 and upper specification is 77.5. Also, we will use same samples as we used in bias and linearity study for GRR study. The study of gauge repeatability and reproducibility study, the most important thing is graphs. First we view the graphs, and when we see these 6 graphs, all of them show that measurement system is very good. The contribution of variation, the parts is maximum, which indicates that measurement system is good. When we see all the points in the range chart are inside the control limits, indicating good repeatable measurement system. When we see mean chart, we see that all the points are outside the control limits, indicating that measurement system is able to distinguish the parts. And when we see operator part interaction, it is also indicating that all the lines are overlapping, that there is no operator part interaction, and hence overall measurement system is good. We'll verify this observation with the statistics. In statistical study of gauge repeatability and reproducibility, we first see the ANOVA table. In ANOVA table, the first thing that we need to see is operator part interaction. The operator part interaction p value is, this case is 0.114, which is more than 0.05, and therefore is insignificant, and therefore we will remove it from our analysis from this table onward. So we see subsequent table, the operator part interaction is removed and it will be removed from all other tables. The second table in GRR study is percent contribution table, which should be seen to understand if percentage GRR is within the limit or not. As per AIAG MSA manual, the percentage contribution should be less than 1%, and we see here it is only 0.38, which is 0.38% means it is well within the requirements, and it's a very good measurement system with respect to overall variation. The third and the final table for GRR study is the most important table. It gives us multiple information which we can see. The first thing that we should see is percentage process variation. The percentage process variation tells us how good is the system for statistical process control. We can see that percentage process variation is only 7.12, which is less than 10%, and therefore excellent system for SPC, statistical process control. The second thing that we should see is percentage tolerance. Percentage tolerance tells us how good is the system for inspection, and we see again it is 7.35%, which is less than 10% requirement, and therefore this measurement system is also good for doing inspection and doing the final inspection and segregating the final products. The third thing that we should see is NDC, number of distinct categories. In this case it is 22, requirement is only more than 4, and therefore we can say excellent system for identifying or distinguishing parts. Also this table gives us unique information. If we compare percentage study variation with percentage process variation, and if they are almost same, which in this case they are, that means our sampling was correct. Our sample was neither obsolete nor short, and therefore excellent system, excellent sampling. Overall, a good measurement system based on a very good sample that we have taken for study. After validating the measurement system, the team identifies the axes or causes which can impact primary metric using process flow diagram, and then screens out the irrelevant axes using cause and effect metrics. The causes or X can be identified by two major methods. One is fishbone diagram, which is useful in identifying causes of an abnormal event like breakdown, or process flow diagram is very useful when we are trying to optimize a process. In this case, team wanted to optimize reactor for yield and therefore chose process flow diagram for X identification. This is the format for process flow diagram, very commonly used in process design, but also is very useful in a Six Sigma project. The first column that we are going to discuss about this format is process step. The process step is a combination of verb and an object. In this case, the verb is removal of leftover and the objective vessel from which we are removing. So we should always write process step in terms of verb and an object. Then we define product characteristic. A product characteristic is the desired characteristic or desired property in the output of the process step. So we see the output of this process step is clean vessel. So what do we want in clean vessel? That there should be no scratch in the inside lining, or the manhole there should not be any crack left, or we can say the contamination free, or there should be no foreign particles in the vessel. So this way, what we define is called as the product characteristics. The next step is to define process characteristics. Process characteristics are the required properties of the 6 M's or the resources which are utilized in executing this process step to achieve the desired outcome. These 6 M's are man, machine, material, method, measurement system, and mother nature. So with respect to man, the reactor operator should have skills to clean. For example, with respect to machine, the cleaning machine should have right liquid pressure. With respect to method, it can be that hand should be or gloves should be moisture free, and so on. These properties are called as process characteristics. Some of these 6M characteristics are not controlled presently. For example, in this case, team found that propanol concentration was not being controlled. The characteristics or process characteristics which are not controlled are called as sources of variation or noise. Together, product characteristics, process characteristics, and sources of variation form our axis or causes. Finally, the cause and effect matrix help us to remove the irrelevant axis. We take all our process characteristic, noise variables or sources of variation, and some of the product characteristic as axis, and try to rate them with respect to reactor yield. If the team feels the impact on reactor yield is high and the relationship is direct, we rate the x or the characteristic as 9, and if we feel the impact is moderate or the relationship is indirect, we rate it 3, and if the remote relationship exists, we give rating of 1, and if there is no relationship, we give a rating of 0. The x's which have rating of 0 and 1 are dropped at this stage, and whatever we are left with is 3 and 9, and we move forward in our next phase with 3 and 9 rated x's. This completes our major phase video. Soon we are going to come with our analyze phase case study video. I request you to kindly give feedback and comments so that we can improve on our subsequent videos. Also, subscribe our channel so that you get intimation about our new videos, and let me know if what topics you would like me to cover so that I can focus my video making around those topics. Thank you very much.